Oh my goodness, it's a chocolate fountain. You've been going for
I'm not.
That's why it's pretty. It's kind of like essentially
Oh, not that.
every decade.
Oh,
You
and
are.
under the.
It's fountain.
Oh, I talk about.
Yeah, like anyone who's going through it, it was,
Oh, yeah.
yeah. I put your fingers in it, no one noticed. So. Yeah, we're gonna have scenario like this week, something. We're gonna have scenario this week.
I don't know, but if you want to know it, I can give it to you.
Okay, you. It's next to me.
We're going to the memorial, the night memorial, the museum. The second day we're doing is one of the.
What is the military thing? The orchestra.
The second day. 2 p.m.
We're going to White House as well.
What?
We're gonna take a picture at the White House.
In front of the light museum.
Yes. That's what that is.
Do I get to meet you, buddy?
Maybe there's a question.
That's funny.
We tell folks I'm on the property.
Okay, we're on page 5. We have yeah, we have one more section to go over. Maybe even start on our quiz review, which I have starting on page 9. Our quiz is Wednesday, but really we're just identifying, applying these rules, and a lot of them are involving use substitution. The one exception is problems that involve synthetic division, but I think they have a certain look to it. We should be able to identify those. So let's recall some of the derivative rules from first semester, and then seeing how they connect with these antiderivative rules that we're kind of just working backwards from. Okay, so we know that e to the u is just going to be e to the u times u prime, right? So that's a first semester derivative rule. And then we also just learned that the integral of e to the u, which is just basically working backwards, right? If this is the derivative, how do we get back to the original function? And we can kind of see where we end up and how we get back to our starting point. And because e to the u's derivative is just itself, the integral is also itself as well. So e to the u plus c. Okay, from first semester, we also learned about natural log, or a to the u. A to the u is like, for instance, something like 2 to the 3x, right? The idea of finding a derivative of an exponential function with base other than e could be 2, could be 4, could be 6. But basically, if I have a constant base raised to a variable exponent, I'm going to use this a to the u rule. And the a to the u rule from first semester we learned is that it still looks a lot like the exponential function, but then there's a coefficient that has to involve natural log to transform it or to adapt to the a to the u. So adapt to a to the u using natural log. So we still have this a to the u times u prime, but in front there's a conversion, and that conversion looks like natural log of a. Okay. So that's first semester as well. The derivative of a to the u is natural log of a times a to the u times u prime. So I want to make sure that we see that it's very similar to e to the u. It just has a little bit of conversion extra in front. Okay, so if I want to go backwards, right, then essentially it's the same, right? So this is the new rule that we're going to learn here. If I want to go backwards, then I know that a to the u is still going to be a to the u, but where's that natural log of a where does it have to go? Imagine I want to take the integral of a to the u. The natural log of a is going to end up where? If I divide it over, it's going to end up in the denominator. Yeah, so it's going to be 1 over natural log of a times a to the u plus c.
It's after the end derivative some like method, right?
Right, once it's been applied. So yeah, so basically we're just starting on this side here. If I ask you where did this function come from? Where does that a to the u come from? You'll say the integral of a to the u is just a to the u. But then because this a to the u is by itself, we have to move this natural log. We have to account for that natural log of a. So it's going to end up in the denominator. Okay, so now that we have these two, or this new rule, we're just going to practice along with the rule that we learned from last week. So remember, natural log of a is a constant. Okay, it's just some coefficient that's hanging out in front. So if I want to apply the integral of 2 to the x, we're just going to apply the rule that we see here. Okay. So no need for u substitution because the exponent is just an x. We can jump directly into the rule here. So what's our a value in this case? 2, right? That's the base. So our antiderivative is just what? 1 over natural log of 2. That's the coefficient times 2 to the x plus c. So it looks a lot like e to the u. It's basically itself, but with a little bit of conversion that has to occur because it's not as clean as e to the u, but it's still an exponential function. It's still going to follow the same idea. Okay, number 2, also exponential function, also the same rule, but this one we have to go through a little bit of what? Not power rule.
Is that through the exponent?
Yeah, it has to do with the exponent. What do you have to do with the exponent now?
U substitution.
Yeah, u substitution. Because if it's just x, there's no need for u substitution. That's just an easy match. But with anything more complicated than an x, we got to go through u substitution. Okay, so what's our u value? Correct. So the idea is that after we make the substitution, we're trying to make the problem look exactly like this. And then once we have it matching like this, then we can apply the rule with no issues. Okay, try that, and I'll come back with the rest of the steps. Okay, where can I put that 4? Outside. Yep. As what? 1/4. Now, this 3 cannot merge with this 4. We can't say 3/4. Okay, does that make sense? Because this 3 is not really a 3. That 3 is attached to that variable, so that 3 is not free to work with or to merge with that 4. So I'll make sure we understand this is a coefficient, that this is something that's part of a function. It should be a perfect match. Once you cover up that 1/4, it matches perfectly here with my A being 3. It's a more specific version of this rule. That A just represents any base other than E. Could be base 2, could be base 5, could be base 7, base 3. Okay, so now I got a perfect match. I can apply my rule here. The 1/4 is going to stay. What's next? X, 1/natural log of 3 times 3 to the U. Let's see. It looks messy, but you just leave your answer in this form. That's fine. One final thing we need to do. Bring what back? Yeah, bring U, replace U back with. Yeah, so what do we put that in place of that? 4x, okay.
1/4 ln3 or
Yeah, so I'll show you couple different versions to do this. Any of these are fine. This is fine. You can even do this. That's fine as well. Any version. You can even have it spread out like this. Raised to the 4x, just replacing U with 4x, and that's so. I think it's good just to know that, okay, there's all these different variations, which is, yeah, the reason why it's good to know is because, if you have one variation and then the multiple choice answer is a different variation, you can just make it turn into, just know that you can match it to the correct or the version that they have on paper without feeling like you got the wrong answer. Okay. Next up. 5 to the tangent of x secant squared x. This is also an exponential function. You've got that base 5 raised to the tangent x. This is too complicated for any one rule to manage. So we know it's got to be U substitution. What's going to be our U value here? Tangent x. Yeah. And that should work out, right? What's tangent x's derivative? Secant squared, right? That's a good sign, right? If you can think about the derivative of the U value and see that version of the derivative somewhere else in the problem, you know that you've got to, you're on the right track. All right, try those steps. Right, so U value is tangent of x, derivative is secant squared x. Solve for dx. We get du over secant squared x. Secant squared cancels out. No leftover coefficient. This matches perfectly with the rule that we want to use. So what's your antiderivative going to be? 1 over, yeah, 1 over natural log of 5 times 5 to the u plus c. And then replace the u back in terms of x, and then this is fine. You can also put the natural log of 5 below the 5. Example 4, it's also an exponential function. You see that base 7 raised to the variable exponent. Also too complicated for any one rule to handle. We got to go through substitution. What could be our u value here? Yeah, 3 minus x squared. Now, if you are looking at your exponent for your u value, we can't pick and choose and just do part of the exponent. It's always going to be the full exponent because we're kind of restricted with our rules here. Our u value, if we want to do exponent for our u value, it's got to be the entire exponent. We can't pick and choose and make it e to the u squared or a to the u squared because that's not part of our rules. So we have to pick the entire exponent if we want to use that as the u value. Okay. Now, if we think of that as the u value, there's a little bit of what going on here. Yeah, there's a little bit of chain rule. We got to be careful there. Okay, let's try those steps. So derivative is outside times inside portion. Outside derivative times inside derivative. So outside derivative is parentheses squared, becomes 2 parentheses to the first power. Keep the inside intact times the inside derivative was 3 minus x's derivative. Good. 3 goes to 0. Negative x becomes negative 1. So negative. Okay there. Okay, I'm not going to FOIL this out. I want to leave that 3 minus x here because I see 3 minus x waiting for us there. So I'm going to leave it in this. I'm going to put the 2 and negative 1 together, but I'm not going to distribute because it'll be easier for me to match if I can keep it in that form.
More like complicated.
Yeah, I mean, if you distribute, you're gonna have to factor this 2 out again.
So, extra steps.
It's yeah, I feel like it's an extra step. Okay, cross multiply. Okay, ready for our substitution. We're going to replace what we have in red, but everything else we're going to keep. All right, do the x's go away? Yeah, 3 minus x can cancel out, right? That's a good sign. But there's a leftover what? Okay, perfect match, right? Now we have a rule to use. Integral of a to the u with a negative 1/2 that's hanging out in front. All right, number 5. This looks a little bit more complicated. 2 times 7 to the 2x squared minus 5, all over 5 minus 7x squared, or 7 to the 2x squared minus 5 x dx. So I see numerator and denominator. I look to see that there's more than one term in the denominator. I can't split this up into individual fractions. So we got to use substitution. What could be our u value? Remember, the more complicated your problem looks, the larger your u value will probably be. Could be a u value where the derivative has a chance to match and pair with another portion of the problem. Yeah, the entire denominator. If we let the entire denominator be the u value, the derivative should produce something that will match with this. Right? Okay, yeah, so
Yes, sir.
yeah, so we're gonna match those two, right? And hopefully everything else will pair up nicely. So here's our u value. Now this is a to the u derivative, so we go back and we think about what the derivative of a to the u looks like. So this is our rule. I'll copy that down above, so and see what rule we're going to be using. Okay, so du dx. All right, one term at a time. The 5 goes to a 0. Okay, so we're just focused on the -7 raised to the 2x squared minus 5. It's my exponential function. So we start off with what? I'll pull the negative in front here. So negative natural log of 7 times u prime for x. Yeah. Okay, cross multiply. The 4x is the u prime, is the exponent's derivative. So 2x squared becomes 4x, -5 goes to 0. So here's my natural log of a times a to the u times u prime. Okay, cross multiply here. So if I want to solve for dx, I got to move all this over to the denominator under the du. Okay, so we have a lot of mess from our derivative, but it's okay because we see a lot of things that is left over that needs to find a pairing for. Okay, copy everything else over here.
That's an extra X before the DX.
Oh, sorry, yeah, that should be here. Yeah, that needs to come over into our next step because we're only replacing what we underlined. That X is still there. Okay, we know that we're on the right track if all the X's can go away. When we get all the X's to pair up and go away. Okay. Can these cancel out? Yes. Okay. And the x's cancel out. Yes. So we know we can move forward. We just have to keep track of some of the leftovers that needs to be part of our coefficient. So what can we push out in front? Yeah, the -1/2 and what else? What else is a coefficient? That's not part of a rule. Yeah, this is also a number, right? Natural log of 7 is not a variable, it's a coefficient. It's not going to prevent us from moving forward, but we also also can't just ignore it, right? It needs to be part of our. So we said -1/2 and the natural log of 7 in front. So and I say -1/2 because I just reduced the 2 and 4. And once all the messiness has been rearranged, we see we have a nice clean rule that's available to us, right? What's the integral of 1 over u? Yeah, natural log s value. Coefficient just stays. And then bring the u back in terms of x. Okay, number 6, we have bounds in the problem, but do we look at them at the beginning? No. So I'm going to rewrite the problem so that we're not trying to do anything with the bounds. We know that we'll do that when we reach the end of our problem, right? So I'm going to rewrite the problem. You don't have to, but I just find that it's nice to not be distracted by the bounds and trying to work with the bounds when we're not ready for it yet. So if this is a problem that we're working on, then there's a little bit of what going on here. First off, do we see that this matches the a to the u rule pretty well? So we got to do a little bit of what though? Yeah, u substitution, right? Okay. Now x over 3 is same thing as what? 1/3 x. It's the same thing, but looking at that 1/3 x just feels a little bit cleaner in terms of the derivative rule. Don't have to feel like, oh, I gotta go through quotient rule, right? 1/3 x feels like that's just an easy power rule problem. Right, what's the derivative of 1/3 x? Just 1/3, right? Cross multiply. Make our substitutions. Okay, we're going to put this 3. Put the 3 where?
So the integral.
Yeah, outside, right? We can't also, I see some students do this, they want to do the 4 times 3 is 12, so we can't merge these together. The 4 is not just a 4, it's 4 raised to the u. So the best we can do is just pull that 3 out in front. Okay. Perfect match with the a to the u rule. Now we can apply that a to the u rule. All right, so the 3 stays. 4 to the u becomes what? What do you start off with? Yep, 1 over now on a 4. Times 4 to the u. Normally we'll do plus c, but in this case, we know there's bounds coming, right? So we'll just bring it back in terms of x. And once we're ready, we can put the bounds in place. All right. What do we plug in first? The -12, right? Does it matter that the lower bound is larger than the upper bound? It doesn't matter. It would matter if we're trying to look at a graph and trying to read the graph, but this, it's fine. Upper bound minus lower bound. I mean, if you really want to, you can change the bounds and then pull a negative outside, but I feel like that's creating additional work that we don't have to do. So it's okay if the bounds are out of order. Things will work out the way it's supposed to be anyways. But if you really want to switch the bounds, you can. Just make sure you pull a negative in front if you want to do that. If you want to swap these two numbers. Okay, I'll plug -12 in for x. -12 over 3 is -4. And then And then 6 over 3 is 2. So this is my answer. In terms of cleanup, that's not, maybe just clean up that 4 a little bit here. Make it 3 over 4 to the 4th natural log of 4 minus 3 times 4 squared.
You want to evaluate this?
No, this is just a number without a calculator. You know, as long as you have all the numbers there, it doesn't matter how you organize it. Same thing on AP exam. As long as they're numbers, if it's free response, it can be as broad out as possible, and you'll still get full credit.
And if it's multiple choice, what do they usually give you like the answer like that?
If it's multiple choice, it'll be, yeah, some variation of that. You just have to be able to match the, you know, match your answer. Okay, let's go to the back page. A lot of use substitution problems here, but I do want to review with a topic that's or a process that is kind of more unique, and ones that okay, these are all basically use substitution problems. I want to go over number 9. So this is a review from a previous topic. So we see a problem like this where we always want to think about, can I just do power rule here? What's the issue with just expanding in power rule? What's preventing us from just,
Denominator?
yeah, denominator is more than one term right now. If it was divided by x, I would just split up into individual fractions and rely on that. But that x plus 3, it makes it difficult to do. U substitution is not going to quite work either, because there's no numerator or denominator u value that will pair up nicely with the other one. So what's the method that we learned? Synthetic division, right? And it doesn't solve the problem, but it will basically do what we want with power rule, which is split up into individual terms. And that's what synthetic division will do. It'll split this up into, or rewrite this problem, individualized terms, and then there's a little bit of natural log use substitution at the end. Okay, so the way we approach this is we set the denominator equal to 0. Once we find that factor, we're going to put that factor outside a half box. And we're going to start putting down our no variables. We're just going to put coefficients of each of the terms. So we start off with what? 2. What's next? 5. What's next? 0. Good. So this is 2x cubed. This is 5x squared. We need a placeholder for the next column, right? And so there is no x power. So we're just going to say that's 0x. And then next is what? -12.
You can subtract the top and bottom rules.
We're going to be adding. We're going to be adding. Yeah. But I'll walk through the rest of the steps here, but any questions up to that point? Do we see why we need that 0 there? Yeah, so we need a placeholder for every degree. So there's a 2x cubed there. There's a 5x squared here, but then it's missing an x. So it's missing an x power, but that's the same thing as saying plus 0x. So for this process, we just need to make sure that if there's any degree skipped over, and if there's no representation of that degree, we'll put a 0 in place of that. All right, so the next thing now is we put the number below, the first number below the line. Right, don't make any changes to it, just drag it down below the line. And now you're going to multiply. Multiply with the factor outside here. -3 times 2 is what? -6. So you're going to put the -6 on the second row, and then you're going to add. 5 minus 6 is -1. Take that number, multiply again with that factor. -1 times -3 is 3. Add again. Multiply again. And add.
That's the remainder.
Yeah, that'll be the remainder. Yeah. So now I'm dividing by x. So what's going to happen to each of these degrees? They're going to fall by 1, right? So there's the x cubed here, right? If we're dividing by x, this is now going to start off which degree? X squared. And then once you have that first degree identified, then just make everyone fall by 1. So this is x squared. This is going to be x. This is the constant. And what's below the constant is the remainder. Remainder just tells us we can't go any further. To indicate what the remainder is, you're going to have a divide by your divisor. Okay. So degree 2, degree 1, constant, remainder. Okay. We can't leave this as our answer. What we've done is we've come up to the starting line so that the integral rules can be easier to apply here than it was over here. Now you're going to put an integral. The nice thing is that these are basically 4 smaller problems, but then these 4 smaller problems are a lot easier to manage than this one long, messy problem. Okay. The first 3 terms I can just apply using what? Power rule. And the last one is a little bit of u substitution with the u value being what? X plus 3. It's going to end up being natural log. Some students can just recognize this and get down to the answer, which is fine. I'm gonna show the u substitution steps, but you don't have to show the u substitution steps for a problem that is a little bit easier like this. So this ends up being just pulling the negative 21 out in front. And then making 1 over u du, which is natural log of u, and then replace the u back in terms of x. So now back to my cleaned up problem here. Every term has been applied power rule. And then this is minus 21 natural log of my u value is x plus 3. So if you are able to look at this and jump from here to here, that's fine. But if you feel like you want to go through the full u substitution to help you see the full process, you can do that as well. So it's up to you whether you want to jump from here to here or show all the steps before you get to this point. Let me talk a little bit about what we're going to be doing tomorrow. So tomorrow we're going to maybe go through more of this as practice. And then if you look on page 7, these are the rules that we're going to have to work towards memorizing. Well, there's some we can remove from this page. And then page 9 is going to be the quiz review. And yeah, these are basically the main rules that we're going to have to make sure that we know.
Wisdom Wednesday.
Wisdom Wednesday, yeah. So we'll have a day to review. And the quiz won't take the full period on Wednesday, so we can probably even spend like the first 10 minutes of class on Wednesday just running through the rules, doing 1 or 2 practice problems before we take the quiz. And then I'll have a help session tomorrow afternoon and Wednesday morning. All right, go get your phones.
Did you memorize the rules?
I'm sorry?
Did you memorize the rules?
Yeah, we got to memorize the rules. Yeah, and I'll tell you, these are the rules that we're going to have to make sure to memorize. Okay.
I mean, is there anywhere I can go to the library?
Yeah.
Check that every day.
Here's what this something like.
Okay.
I never done first detail. I'll bring that to you.
Okay.
Sure.
Yeah.
On Wednesday would be something good.
Logan.
Yeah. Yeah, I'm saying
It's when it's like math.
That's okay.
It was something.
It's good.
Like.
Yeah, good job.
Didn't go.
Yeah, I've never been there. I've never been there.
Was it your first choice?
For school, no, it was really good. The debates professor, they were like,
SATs more. Yeah.
like, if you're not going there for music, like, you wouldn't be on there because the rest of the campus is like dead. But the music school's great.
What's your first choice?
It's even Eastern School Music, which I'm auditioning for this Friday
Yeah.
in Rochester, where I'm from. You're a Bills fan, you know.
Right. That makes sense.
And then Florida State's the other one.
Florida State, okay.
Professor there is really good. And it's also a huge campus environment.
Yeah.
Let's go to you good.
Went to Emory.
Oh, you go to Emory? I go there every week for my orchestra.
Oh,
Okay, you work for there.
Oh, thank you.
English section, but I.
That's cool.
That's kind of a fun drive.
It is a long drive. I think it's worth it because of the whole music.
Yeah. Good.
Lots of folders is nice too.
Yeah, nice.
I don't know if have you ever been to a concert?
I have, yeah. That's really nice.
I took this like
Yeah, never,
And
Dallas
they
like,
didn't
it's
tell
like
me
flat,
they
it's like super.
Yeah,
flat.
yeah.
Once in and out the first time.
About that,
Oh,
I was
wow.
like,
Yeah, that's a good place.
Yeah.
thanks.
Ever been there before?
Dallas?
I feel like I've driven through, I don't remember
Anything about Dallas? No.
My takeaway was that I had good food.
Yeah, they're good food. Okay, nice.
I mean, everything you ask, like, whenever a place has a raisin canes and now the same velocity, you know, you're pretty percent.
Yeah, we don't have either of these, so that was together.
Still.
You going, like, you have a support party?
Yeah, my parents will do something just with our families. My dad loves watching Super Bowl, so we're gonna have a get together.
We're rooting for, I'm rooting hard for 49ers.
Yeah, he's a 40, he likes 49ers too.
I'm pretty sure too.
I'm surprised 49ers are favorite to win.
Yeah, I guess it's like an all around better, maybe a better team. They have more like skill players.
Like,
Really?
It's kind of like, honestly, is like, I think the Chiefs still have a good shot too, honestly. It's kind of like the Eagles last year. It's kind of like them a little bit.
that was why we're watching it now.
Oh, where they were favored.
Yeah, like the 49ers are very similar to like how the Eagles were last year. They kind of. Everyone's
It's just interesting because like
I think
an average person would have a hard time
That's why.
naming anyone on the 49ers.
Yeah.
Meanwhile, someone has an easier time naming players on the Kansas City Chiefs.
Yeah, oh, Patrick Mahomes.
Right. So it's surprising that 49ers are
Yeah,
favored.
what's kind of annoying though is like, people are game, fucking Taylor Swift's gonna get to the game.
Yeah, she has a tough life.
I know, like that. It's the worst, the national game itself.
Right, I know.
Like, oh my gosh.
I'm just gonna.
I wasn't 49ers, like,
Get out.
yes, 49ers in the NFL, I think it's fucking good.
Fine, yeah.
Thank you. Thanks, guys.
I'm not making. I'm getting sick.
Or, yeah, or 10 before you.
Yeah, I know. I can't do it.
So many other games. Oh.
Was that such a?
I'll see. Yeah.
Oh, I got it.
Yeah.
And your phone, there's. Thank you.
Like, I got it letting like, I got oh, it's your rock. It was the same one I did it yesterday, but like, I didn't remember any.
Did you get like the equation or the space? I don't think they had the same height.
Yeah.
Oh.
That's not that bad.
Oh my God.
For number two.
It's like, no, they have the same height and then.
Please just make a note to include integral notation.
So they do.
They say-
I think I can get.
Yes, that's it. They had the same max displacement at the same time. That's why I literally locked it.
Like the rest of it.
The rest of it, I was like,
Hold on.
Explain your answer.
Yeah.
The equation is an error. I'll say this is an error. I don't know.
Oh, yeah. Wait, it's multiple.
Like, I'm not being like, you're saying.
No, it really said so. It was about like what is producing value.
Didn't get back until Saturday night, so like I had no time. And then I did it because she makes it read that means that I feel like.
She said like.
Yeah.
Next 30 minutes.
Off like,
Concerned about like. That's in front of the so if you have to run out.
Two more captains.
Yay.
Well, I can be here.
It's like, it's been like.
Yeah.
But you know, Jack, the joke is, you don't even really make it.
I joke about it.
No.
I can't.